Welcome to another Thermal Analytics webinar. Today's webinar is Exhaust Streams and Component Heat Protection. Tim Viola, an application engineer at Thermal Analytics in our headquarters up in the Upper Peninsula, will be doing the demonstration webinar. And Tim has a good background in thermal management as well as heat and signature management. He's worked on transportation vehicles of all kinds, commercial and military. Tim's also got some broad experience in electronic wearables and seat technologies, but we're going to be concentrating on exhaust streams today. A new technology at Thermal Analytics and a real time saver for any kind of automotive engineering heat management. I will field any questions you have at the end of this broadcast, approximately in a half hour. Just go to your Q&A box and type in at any time, and we'll field as many questions as we can in the time allotted. This webinar will be recorded, and the slides, the presentation will be available too, usually within 24 hours. Tim, are you ready to start the webinar?
Yeah, all set, Keith.
Okay, thanks. Go ahead.
And thanks again, Keith, for the introduction. Hello, everyone. All right, so today I'll be taking you through an example of how the exhaust stream feature can be used in some of your design efforts. Oh, something's going on here, sorry. Okay, there we go. Sorry about that. I'm having technical difficulty here already. All right, for this demonstration, we'll address some hot components in an engine compartment, and then we'll take a look at some of the updates that were made to the exhaust stream feature in TAITherm version 12.5. We'll then take a look at implementing a fix for our hot components, and we'll see if there were any side effects that may have come up because of it. For this model, we'll want to assess the temperatures for some components packaged within an engine compartment of a twin-turbo V8 sedan automobile. You can see these components highlighted as red within the image. These include the battery, some fluid reservoirs, and a fuse box. We will be modeling a transient warm-up case. The vehicle will start and be initialized at a temperature of 20 degrees Celsius. The vehicle will then be turned on and the engine and exhaust components will begin to heat up. The model will then be run for a 30-minute transient case with the vehicle traveling at 120 kilometers per hour. Let's take a quick look at the thermal model. Here you'll see we have some major heat contributors, including the engine, the cooling pack, the transmission, and most importantly, the exhaust. This is where we'll focus most of our attention, as it is most likely the largest contributor to our problems. For those new to the feature, the exhaust stream automatically calculates the convection coefficients in the pipes, catalytic converters, mufflers, and silencers based on an engine RPM, exhaust gas temperature, and exhaust gas mass flow rate. For those in the audience that may have worked with the recent versions of our software and had some time to use the exhaust stream feature, we'll take a quick moment to look at the improvements that we've made to it. Improvements have been made to the exhaust substreams, granting the user a much more simplified approach to choosing inlets and outlets of a stream. There are now 3 options to handle this. There's the single inlet, single outlet option, which was the old method that is still available in 12.5. This would be acceptable for any straight section of pipe in your exhaust system. There's 2 new options, however, in 12.5, and that includes the multiple inlet, single outlet option, which will be used for the start of our stream from our exhaust manifold with multiple inlets to a branch point along the exhaust network. And the other option is a single inlet, multiple outlet, which will be used from the branch in the exhaust network to the end of a dual exhaust setup. Let's take a quick look at how this would be applied to our thermal model. So these improvements made in 12.5 really simplified setting up the exhaust stream. This model was featured in other content that we've provided, and after updating it, the number of components went down from 18 to 11, the stream points dropped from 22 to 13, And the big one here is now we only need 2 substreams compared to the 17 we needed from 12.4. The model we are looking at will only need, like I said, the 2 substreams, one multiple inlet single outlet, followed by one single inlet multiple outlet. So let's take a look at how this would correlate to our vehicle model. Here's a better look at how this will be set up. In the upper left hand, shown in the blue box, you have the exhaust manifolds, where the multiple inlet single outlet substream will begin, ending at the branch point in the middle. From there, in the yellow box in the upper right, a single inlet multiple outlet substream will be used from the branch point to the exhaust tips. These are the only substreams that are needed in this model for the entire exhaust system. So let's take a quick look at the thermal model and look at some of the finer details of how this is actually set up. So here you'll see our thermal model. I'm going to simply isolate our exhaust network here. Turn on some part colors quick and just show the fluid nodes. So why don't we start from the upstream portion of our network here. So here you'll see some intake boxes. We just have a simple fluid stream here to the turbo. That air from the turbo will then go to the engine, and then after that, this is where our exhaust stream part will actually be applied. So if we look at our parts editor here, you'll see the same dialog that we saw in the presentation here. So we've set some of our values. I think the one to note here is we are, like we said, ramping up a transient case. So we did supply a curve for the exhaust gas temperature going from ambient to roughly 700 degrees in the matter of a minute or two. Outside of that, if we start looking at our components, like I said before, these went from about 17 to how many ever you see here, I think 12 roughly. And so the first one being is our manifold. So a manifold would have a pipe type of a exhaust component, and the reason why we need to make this separate from the rest of our pipes in this network is because of our node spacing. Because we have some intricate geometry here, when we want to capture all of these curvatures, we want to make sure that we use a smaller node spacing than what might be used in other portions of our pipe. So here you'll see we've used a node spacing of 15 millimeters. Next, you'll see we have our turbo, and we want to make sure that we updated that to be a turbocharger exhaust component type. And you'll see here that we're just going to use our built-in calculated heat rate option for the compression and expansion and volute process here. You'll see that we need to specify a max and inlet diameter here. And if you actually highlight over these, you'll kind of see what a graphic as to what the input should actually correlate to. So see if that for the max outer and for the inlet outer. And again, this turbo was broken up into 2 parts. There's another part here, and you want to identify an expansion and volute section of your turbo. All right, so next we have the pipe from the turbos to the silencer. So you'll see here that we can specify the entire one component for the entire pipe here as long as we want the same node spacing. So we actually bypassed our catalytic converters here. So the next component that we have would be the catalytic converter, right? And again, we're just going to use our built-in heat rate functions to calculate this. And I put in a couple nominal values in for cell density and cell wall thickness. There are a couple of bounding part options you can use. So right now I've just specified a brick here, but you could also have an air option as well if you had a more intricate catalytic converter. So we'll bypass these 3. These are just the mirrored other side of the exhaust network. But why don't we take a look at our silencer here. So our silencer would be just a muffler type of a component. And here you can specify the number of chambers you want. So this muffler was broken up into 3 parts. And each of these parts was then identified as one of the chambers in our exhaust muffler component. The next will be the split to the exhaust tips here, and this is specified. Again, we can break it up to all the portions of the pipe. We didn't have to make these their own individual. If we wanted to maybe have a smaller node spacing, we could have done that, but for this model I just used the same node spacing. So again, you can bypass other components in your setup until you want to specify maybe your muffler right here. So here is, again, another, similar to how we set up the silencer, is the muffler. And this, again, includes 3 chambers. I think another thing to note here is that for each chamber that you have, you will get 1 node at each of these. So it's important to know if you have an intricate muffler or something you want to set up, you'll want to make sure to break that up accordingly. So now we've hit on all the components of our network. Why don't we take a look at the stream points? Prior to this, the stream points, you need to identify a lot more for many more sections of your exhaust network. So if we take a quick look, I'm just going to choose all of them, quickly go to wireframe mode so we can see through some of the parts. And you'll see that the only stream points that we need to identify were the inlet stream points, so all of the inlets at our exhaust manifolds. We have a total of 8 for all the 8 cylinders. The next one would be we want to identify 1 at a branch point. So we have our multiple inlet to single outlet here. And then from our single inlet, we have a multiple outlet here. So we'd have 4 selected for our outlets at our exhaust tips. So the next one is our substreams, right? And this went from, I think it was 17 down to 2, which is pretty drastic here. And again, kind of what I just covered, but if we selected from the exhaust to the split, you'll see that this just selects our multiple inlet to single outlet substream. And you can specify now your inlet points here through this dialog, and then your outlets. So we just have 1 at the pre-silencer merge here. So now, if we take a look at the split to outlet, same thing here. Our inlet will then be that merge pre-silencer stream point, and then we specify our tail out as the outlets. And there's new functionality for distributions. This should have said 25% here. I must have clicked something so it changed it, but you would see that the flow is all 25% to each of these, but there is functionality to change how that would split up as well. Okay, so now that we're back to the PowerPoint, if you're interested in more information in regards to the exhaust tool, again, feel free to visit our website or send us questions on any of the particulars for how we set up maybe some other exhaust streams. Okay, so why don't we take a look back at our engine model here with our full vehicle. So knowing where to place some of these components in an engine compartment might be a difficult task if component heating becomes an issue. TAITherm can help aid in these decisions as well as determine potential problems. This can give the engineer a quick assessment on how they might go about fixing the issue. So some of these components are obviously getting too hot due to their close proximity to the exhaust system. This includes the battery, the fluid reservoirs, and the fuse box. So for these components, we've set a design temperature of 100 degrees C. And let's take a look at the thermal model and see some of the details on how this can be set up to evaluate this case. So I'm going to show the entire vehicle here. I'm going to hide some components so that we can see the engine compartment. And we'll go to the post-process tab here. And you'll see, we do in fact have 30 minutes of transient heating. So I'm just going to go to the end time step here and take a look at our model. So like we said before, we have some components that are obviously getting a little hot. We have our upper bound limit of our temperature set to 100. So anything you see here in red is kind of getting to where we were thinking that there might be some issues. So if we take a look, I can click here and see some of the temperatures. And what we're going to do now is we'll take a look at changing the display mode, and we'll take a look at what's called relations. We change this. It needs to read the view factor file, and this is going to give us a way to visualize the radiation exchange between elements or parts in our model. So once this loads, We'll move on to the Relations tab here. And here you can see, if I change my upper limit here real quick, you can see that it's pretty self-explanatory, right? This exhaust pipe being close proximity to this reservoir, it's getting very hot. So what maybe you didn't notice, though, if you were using this visualizer here, is you can see some of the distributions on the left-hand side in this table. Maybe if we took a look at maybe the fuse box up here, you'll see that the fuse box is getting hot in this corner, and you'll see that this is actually more in close proximity to our turbo. So you can kind of see how this breaks down then. So the turbo is a bigger factor for this part. So maybe that's something else we'll want to address. So if we take a quick look for that 100 degrees C design temperature that we've set, under the summary table here, you'll see that I've set a design temperature for some of the components in our model. Now, I only specified them for just a specific portion of these components, but in your models you might have hundreds of design temperatures you might want to compare to. But just for simplicity's sake, I just picked the few that I knew were going to be causing some issues. So if we took a look at this, I selected those from the summary table, so you can kind of see the ones that I've isolated, right? The ones that we just talked about. Okay. So why don't we take a quick look at the results from a thermal report that I went ahead and generated in the model. Thermal reports can be configured a number of ways to output data for many models. They're very helpful for this component assessment. So why don't we open our report that I generated prior to the webinar. So this is our baseline results. So here, this is a HTML format that's just a compiled version of everything that I output from our thermal report. So our first item is a table of any items that exceeded the 100 degree Celsius design temperature threshold that I specified, and just by how much that they did fail that requirement. So anything that fails will show up here in this table, and anything that passed that I set will not. The next portion of the report template, or sorry, the report is the actual temperatures for the max temperatures for all those components that we specified, followed by what we'll look at a little more is a plot of these. So you can see our design temperature 100C and when in time these did indeed fail. So almost everything is failing here other than one component, which is the rear bumper, which a little bit of foreshadowing, we'll see how this changes as we change some of our design up in some of our exhaust components. So there are a number of options that we could take to try and fix the issue, but why don't we take a look at substituting a double-walled exhaust pipe from the turbos to the catalytic converter. So we'll add this by simply making the part a multi-layer part and updating some of the material properties for these layers here. So I went ahead and made these changes prior to the webinar and have already computed the thermal results to save some time. For anyone interested for this model, this 30-minute transient model takes less than 30 minutes to run on my work desktop here with very minimal allocated processing power. So we can then evaluate these components again using our same thermal report from the baseline model assessment. So if we look at the results for the updated model with the double-wall exhaust pipe, you'll notice on the parts are now some of the maximum design temperature threshold were not reported as having failed. So the fuse box still exceeds this threshold and still failed, however. So as we discussed before, this part has a greater influence by the turbo manifold than the other components. So maybe we'll want to make a new change here to address this part. So let's also try adding some insulation to the turbo on the hot side. Again, this is simply done by creating a multi-layer part similar to what I did for the exhaust pipe and adding the insulation material properties to that part. This model was previously configured again to run and save some time. So now you'll notice that the parts in question are now well within the design temperature threshold. So again, on the left here is our baseline, right? And on the right is our components that we've been addressing. So you'll see here, this time now, the bumper is actually failing. And this is due to, because we're blocking all the radiation exchange early in the exhaust network, this resulted in hotter exhaust temperatures towards the end of the network, causing the bumper near the tailpipe to exceed the specified design temperature. So you might want to take a look at some of the design changes you make. If you set these monitors up properly, or these design temperatures up properly, it can help you assess your entire vehicle on the fly. So adding insulative layers was just one of many solutions that we could have evaluated. It may not have been the most cost-effective or the most timely manner to implement. So many others could easily be implemented in the model, each taking little time to set up. Other than the two that were already assessed, the user could model a way to redirect ambient airflow to some of these components. They could change the surface emissivity of the critical components so they receive less thermal radiation. Maybe they want to actually change the surface emissivity of the exhaust turbo so there's less outgoing thermal radiation to impact these components. Maybe we wanted to actually add some geometry for shielding between these components and the hot exhaust, or maybe we actually wanted to translate some of these components further away from the heat sources. Or maybe we actually wanted to reroute the exhaust pipe and implement new geometry. And maybe you wanted to assess multiple fixes at once. You could do all this in fairly little time. So in conclusions, the TAITherm is well suited to assess component temperatures in a vehicle model. The exhaust stream feature can handle convective heating in an exhaust network with minimal required model setup. The exhaust stream modeling has been drastically simplified, and we're continuing to do so, which also results in easier model setup. So just for everyone to know, TAITherm 12.5 will be available December 12th, and there are also some additional features, including ways to post-process some of the exhaust stream, as well as some enhancements made to thermal links. Thank you for your time, and I'd be happy to answer any questions you might have.
All right, thank you, Tim. Let's bring up some questions here. One question we have is this exhaust stream's a separately priced license?
Yes, I do believe so. I'm not sure on the details on that, but yeah, that'd be something that maybe we could send out to our customers that are interested.
Yeah, and certainly can call our sales office,
Sure.
Or if you have an account holder, either one can help you with that. I just want to remind you that we do have a repeat to this webinar. It'll be another webinar put on by Tim at 1 o'clock Eastern time today, 1 p.m. Eastern. And anytime you do sign up for a webinar, even if you aren't able to attend, you will be getting the recording and the presentation. So I encourage you to sign up for these webinars. Other than the webinar today, I believe the next webinar will be in January when we start to show some of our new 2018 features. It looks like we don't have any questions, and so like I said, we call our sales office if you want more information. Tim is also one of the key support staff, so whenever you have technical support questions, often Tim is one of those that will help you. So you could ask for him specifically if you have questions on setting up a model for the exhaust streams as he demoed today. Thank you, Tim, and thank everybody for coming, and look forward to our next webinar. Goodbye.